Not that it really matters because this is the last day, but let's do it anyway. So we've got t equals t0 over this whole square root 1 minus v over c all squared thing. This term down here shows up in special relativity all the time. It's going to show up today when we do mass and length and see how that happens. This thing gets, like so many other things in physics, gets shortened, gets condensed into a single factor that we call gamma. This symbol right there. It's like a fish. Fish is falling.
Everything under the root?
The root and everything in it. So then we could rewrite this whole thing as t, the time on Earth, is equal to the time on the spaceship divided by gamma. Or we could say that, we could rearrange this thing really easily then and say that t naught is equal to gamma t. Because this term shows up so many times, we just abbreviate it. Say that, yeah, gamma is just the square root of 1 minus v over c squared. This is the factor that determines how time dilates. It's also going to determine how mass and length are impacted. So like I've already done up here, we can write the time dilation equation much more simply in these two forms. I'm just going to draw an arrow. These are the simpler forms. So that's the kind of thing that might not actually be a bad idea to throw onto your formula sheet. Down here at the bottom, the existence of this gamma factor, gamma equals the square root of 1 minus v over c all squared. So that I can rewrite this as t equals t naught over gamma, and then this one can be rewritten as t naught equals gamma t. Is something that you might want to consider doing. I hope you've left some space over here because we're going to do some stuff with mass and length today. Oh, lid. So we can use the time dilation factor to analyze things without actually finding their values. We can figure out, using the time dilation factor, how time is going to change. So how much will 1 hour of time dilate in each of the following situations? So you're walking at 2 meters per second. This is Zach's degree, his degree in walking. So the time dilation factor, if we look at what's going to happen here, square root of 1 minus 2 over 3 times 10 to the 8 squared. This 2 over 3 times 10 to the 8 is basically going to be what? 0. Effectively, it's going to be 0. If you need proof, I can jam that through my calculator here. 2 divided by 3e8, e8. 0.00000007. Very small. Okay, it's effectively 1, because 1 minus 0, and the square root of that is just going to give you 1. So how does time dilate while you're walking? Doesn't. Even as a race car, 70 over 3 times 10 to the 8, and then we're going to square that. It's the squaring it that makes it astronomically small. That's still going to be 1. In a race car, it doesn't really change. There's no active time dilation in it for an hour, really. The SR-71, the fastest man-made production jet that they have sitting at the Seattle Flight Museum, which is awesome jet. Even that one, I mean, we can start running these numbers here. 1 minus, this is going to be 1 times 10 to the 3 over 3 times 10 to the 8. And we're going to square that. I'll run the numbers for us. We're going to have 1e8 over 3, 1e3, sorry, over 3e8. It's very small. We're going to square that. 1 minus our answer is just 1. My calculator says 1.
Is it just because the answer is like so small?
Well, this term right here, after I squared it, was 1 times 10 to the negative 11.
Yeah.
So 0.00000000001. Okay, so things start to get really small. The Earth around the sun, though, now we're starting to get into velocities that are a little bit more substantial. that time dilation factor ends up looking like this. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then a 5. So even then, it's really small for an hour's worth of time dilation. The Earth Sun flying through the galaxy, that's substantially faster. That only gets changed like this. 1, 2, 3, 4, 5, 6. 2, 4, 5. Yeah, just start calling names. Protons at Triumph. So Triumph is UBC cyclotron. If you do a physics degree, anywhere in the Lower Mainland, U of V, SFU, UBC, it is likely that the Physics Students Association will do trips out to Triumph.
Oh,
If there's cyclotron, in that cyclotron, you get protons moving at 2.24 times 10 to the 8 meters per second. Even that gamma is going to equal 1.5. This is the time dilation factor. Sorry? Well, if you think about what we did, we took all of those hours over an entire year to get a measurable amount. This is 1 hour. So the time dilation for an hour isn't much. But for a larger period of time, the dilation is going to be larger. God, I hate stupid flying. The muons at CERN. Hands up if you know what CERN is. Only one of you knows what CERN is. That saddens me a little bit. CERN is the home of the Large Hadron Collider. The LHC, we know what the LHC is. Yes, CERN is its home. So muons are a class of particle that get shot around this very large particle accelerator, smash into each other, and decay into all sorts of crazy forms of matter. This is how we figured out the Higgs boson was a thing. Even at those speeds, 2.996 times 10 to the 8, we're almost at the speed of light. 19.4 becomes your gamma factor. Then you got the fastest one. We've got the electrons at the Stanford Linear Accelerator. Stanford is in, I want to say California? Where's Stanford?
It's in the U.S.
It's in the U.S., American University. They've got the electron linear accelerator. So these things aren't going in a circle. They're just going in one long line, then they hit something and explode. Decay and all sorts of cool stuff. The difference here, I mean, we went from 2.996 to 2.9979. All of a sudden, that Lorentz factor, oh, I didn't even call it that, but that's what it is. That gamma factor starts getting larger and larger and larger. Very, very quickly. I am going to flip back here. I didn't specifically say it. This gamma has a name. It is called the Lorentz factor, which I should have introduced it to you earlier, named after a scientist who first suggested its existence. Lorentz was a physicist, mathematician who was he developed a really convenient way to translate from, because we were talking about reference frames, yeah? So to translate nicely from reference frame to reference frame. So we call, and there's a really easy way to multiply it, which I'm not going to teach you because the mathematics, I say easy, but it's not, but it is. We call them Lorentz factors. How do you convert from reference frame to reference frame? This is your first example of it. By multiplying or dividing by this Lorentz factor, it will take you from the spaceships to your observer, or from the observer back onto the spaceship. So we've looked at time already. There's another piece to special relativity that deals with something called length contraction. And even just saying that is like, excuse me? Well, you've kind of already seen it. When you're traveling at or near the speed of light, one of the interesting effects that we looked at yesterday was that space itself shrinks. Because one of the questions I gave you, one of the examples said, okay, well, how long? We know that the distance from Earth to Alpha Centauri, 4.24 light years. But at the distance as measured by the people on the ship traveling faster, substantially faster, a significant fraction of the speed of light, they actually measure that length to be shorter than it is. And that is a concept called length contraction, where the physical space that is occupied or not occupied, the universe, when moving at or near the speed of light, shrinks. It does.
Go back.
Yes. Because at rest on Earth, we see it's 4.24 light years. Spaceship measured it to be 3 point something. You can't, like, both of those they have to both be accurate. Like, not one of those is wrong. So what happens? The explanation is that space-time changes when you're moving at or near the speed of light. Okay. Without going into a lot of mathematical detail as to why, I'm just going to state it for you. The prediction relating to the length of a moving object. The length of an object is measured to be shorter when it is moving than when it is at rest. This shortening is only seen in the dimension of its motion. Okay? So it's not like the entire thing shrinks. Its height stays the same. It just gets skinnier if it's moving that way. The length contraction looks like this. It's a similar equation to time. It's written as L equals L naught times the square root of 1 minus V over C all squared. This term shows up again. This was our gamma, our Lorentz factor, named after Lorentz. So I can rewrite this thing as L equals gamma L0, or L0 equals L over gamma, which we're also going to toss on our formula sheet. I'm just going to toss one, not both. This one here. L equals, actually, I will do two. L equals L0 times the square root of 1 minus V over C all squared. And I'll write it like this too. L equals gamma L0. So there's a slight difference now between the length contraction equation and what's it called? The length contraction. Time dilation versus length contraction. Time dilation is T equals T naught over square root of 1 minus V over C all squared. And the length contraction is given us by L equals L naught times this factor here. Where L0 is the length at rest, and L is or at rest or as seen from inside the object. And L is, we sometimes call it relativistic length. Or as seen from an outside observer. Sorry. So the standard, I mean, it's the same as with how we defined L and L0 is the same as how we define them for time. T was, you're standing on Earth, this is the time you observe. T0 is the time that is observed inside the fastly moving object. Same thing here. L is the relativistic length. You're standing on Earth, you see the USS Enterprise fly by at almost the speed of light. How long does the ship actually look? Sorry, how long does the ship look to you? That is L. L0 is, how long is the USS Enterprise at construction? For those of you who have not watched any Star Trek, that's the name of the ship. So, how long would a meter stick, this stick right here, if I were to somehow project this thing past you at 99.5% the speed of light, somehow, I just throw it and it goes, okay? How long does it look to you? Well, let's do it. I want to know, we want to know L. How long does the meter stick look to the observer At rest, that meter stick was 1 meter. Well, we know that L is equal to L naught times the square root of 1 minus V over C all squared. We know that C is 0.995, or sorry, V is 0.995 C. So we're going to get L is equal to L naught times the square root of 1 minus 0.995 squared. If you weren't here yesterday, you just take, we use the velocities as percentages of the speed of light c. My c's are going to cancel as soon as I shove this in here. So we're just going to get this 0.995 squared coming out there. We know L is 1. L0 rather is 1. How long does this thing look? 0.099, so the 9 meters. So this meter stick at rest is a meter long. 0.099 meters is how long?
Like 9 centimeters. Or
10 centimeters. So you see it as traveling at, do it that way. It's that long between my finger and my thumb. But it's not like, and then the temptation is to say, oh, well, we just chopped off, that you didn't chop off the meter stick. The entirety of the meter stick gets condensed to that length. It would say 0 to 100 between here to here, and it would still remain accurate. Because things get wacky at or near the speed of light. Sorry? Space itself shrinks. It's not just the object that's shrinking, it's space is shrinking for the object.
So that's, so at pretty much 99.5% of the speed of light, it's not like it seems like it's 10 centimeters, but it is 10 centimeters. No, it is 1 meter still.
It's a 1 meter length.
Yeah.
You see it as looking at 10 centimeters long, but it's still the entirety of the meter stick.
Yeah, but like if you were to like take a snapshot of time,
if you took a snapshot of it, it would look like if somehow you had a ruler behind the thing, and we were able to catch a picture of this thing, it would look like it would be 10 centimeters long.
Okay.
That's how you would see it. That's how you would observe it as a rest observer. As an insect riding on the meter stick, traveling at 0.995 c, the insect would tell you, no, this thing's a meter long. If it walked from end to end, it would have walked 1 meter. But we see it as having walked 10 centimeters. Because that's the length that we see. Yes, and that's the other thing. It would maintain this dimension. It would remain this tall. How are we doing back there, guys? We good back there? Toby and yeah. Yeah, but the problem is you got to slow them down. As soon as you slow them down, then
you don't need to slow them down.
just keep them going, eh? Okay, so an 85 meter long spaceship passes you at 2.23 times 10 to the 8 meters per second. How long does it look to you? Go. This is an application of the exact same question. What do you get? Sorry? 56.9, yes. The 85 meter long spaceship passing you at 2.23 times 10 to the 8 meters per second will look 56.9 meters long. Absolutely. So everything you've seen in Star Trek or Star Wars, when they're going fast and they get long, that is exactly backwards. Yeah, it looks like they stretch, but it's like, no, that's not what would happen. It would go, phew, take off. Cool. It looks cool, but that's the problem with lots of things. Sometimes looking cool is absolutely the wrong thing to do. There's parallels to life there as well. So, sometimes looking cool is the absolute wrong thing to do.
My dad's been watching the whatever one on
Hold on, let me keep going. I want to hear that after. Okay, so we can do the same kind of thing we did yesterday. Suppose a spaceship is 100 meters long when stationary. When it moves past an observer, the observer measures the spaceship to be 25 meters long. How fast is the spaceship moving relative to the observer? We can set this up the same way, except now we're looking for v. I'll just run it through for you guys. We have L equals L0 times the square root, unless you want to try and beat me, v over c all squared. I can divide L0 on both sides. I can square both sides. I'm going to subtract this guy over and add this guy over. So I'm going to get v over c all squared equals 1 minus L over L0 squared. I'm going to square root that and multiply it by c. So we're going to get v equals c times the square root of 1 minus L over L0, which looks an awful lot like what we did yesterday. And I'm going to run that through. C, we can just call it C. L is the length observed, and L0 is how long the spaceship actually was when it was constructed. What you're going to find is that the velocity to shrink the ship, 0.9682 c. So you got to be going 97% the speed of light in order to make a 100-meter long ship look 25 meters long. Hey, Mr. Go, what's going on? Matthias is the only one here. You can have him. Yes, L0 would be 100. And the 25 meter long is L. Cool? We did this question yesterday. A certain star is 15.6 light years away. We didn't do exactly the values, but how long would it take a spaceship traveling at 0.95 c to reach the star, as measured by a stationary observer, as measured by observers on the spaceship, and what is the distance traveled according to observers on the spaceship? We did this yesterday using Proxima Centauri. We're going to do it again using this star here. So to find how long it would take traveling at 0.95 c to reach the star, as measured by stationary observers on Earth. This first part of the question is just standard d equals vt kind of stuff, because everything is measured from on the ship. Sorry, everything is measured from on the Earth. Earth says it's 15.6 light years away. Earth says the ship's traveling at 0.95 c. How long does it take to actually get there? Well, t equals d over v. 15.6 light years is just 15.6 c years, divided by, we're told, 0.95 c. The c's are going to cancel, and we get this thing taking a journey on, as seen from Earth, yes, of 16.4 years. How long does the spaceship crew think that they actually take? Well, now this is time dilation. Earth sees them as traveling at 16.4 years. So we want to find the time as observed by the people on the ship. So we're looking for t0. So we know we had an expression on our formula sheet. t0 is equal to t times the square root of 1 minus v over c all squared. That's how it's written on the formula sheet. So we're going to get t0 equals 16.4 times the square root of 1 minus 0.95 c over c squared. What is our t0? How much time does the spaceship crew observe? 5.13 years. Absolutely. So that's what they observe as far as their time is concerned. The one thing that remains consistent is they also see themselves as traveling at 0.95 c. So we could say part C to this question is, well, what distance traveled according to the observers on the space station? They see themselves traveling a distance of their velocity times the time that they measure. They see this as being v, 0.95 c, times 5.13 years is equal to a distance of 4.871 light years. So the Earth sees the star as being 15.6 light years away, but the ship sees themselves as only having traveled 4.871 light years. That's weird, and that's how we did the question yesterday. We can do the exact same question using length contraction. Because we can set it up the same way here. L0 is the original length at rest. So the original length at rest from the Earth to that star was what? 15.6 light years. We're dealing with the distance. The L is whatever is a distance. It could be the spaceship that's moving past you. It could be the physical distance in space between 2 points. L is the relativistic length. And we know that V equals 0.95 c. So we can say that L is equal to L naught times the square root of 1 minus V over C all squared. So this is going to be 15.6 times the square root of 1 minus 0.95 squared. What do you get for the relativistic length? 4.871 light years. So you can verify this several different ways. We can use time dilation and d equals vt, or we can use length contraction, which means what I said at the beginning of class is true, that for an object moving quickly through space at or near the speed of light, the space that they're traveling through is compressed relative to what it would be if they were slower. So you want to get to Mars faster, you just got to travel. So you want to shrink the distance to Mars, you got to travel faster. So, I mean, there was criticism in Star Wars. We're going to nerd out a little bit here. Han Solo claims that the Millennium Falcon can travel the Kessel Run in a certain number of parsecs. People watching that would say a parsec is a unit of distance. So what he's comparing it to is a length of time given to you as a reference of distance.
It just sounds cool.
It sounds cool, but there's some relativistic ideas here. What he's suggesting is the Millennium Falcon can do it so fast that it's actually covering less time to do the same run. Length contraction. Han Solo is claiming special relativity at that point.
When they go like hyperdrive or whatever, are they going the speed of light?
I think that's what they're claiming.
That's what I'm saying. That's what
Light speed.
Light speed then?
But they're not. So, what does this mean for an object that travels at the speed of light, like a photon, a particle of light? For an object that travels at the speed of light, L is equal to L0, which is the square root of 1 minus, in this case it's going to be C over C, all squared. C over C is 1, 1 squared is 1, 1 minus 1 is 0. L0 times 0 is 0. So for light traveling from a distant star to Earth, it doesn't register the time between the star and the Earth. It's just there, or the distance rather. It's just there.
So like,
But it doesn't, because we observe it traveling.
so
But from its perspective, it's just there. If you ask the photon, oh, how long did it take you to get here? Like, I just got here. Like, I'm just here.
like, yeah, there's
Took me no time. How much space did you travel? None. No space. But from Earth, we would say, nah, 15.6 light years. This is special relativity, Nathan. This is special relativity. I'm sure it can't break down mathematically. We did math to get here. I've been proving this to you every step of the way. It is not a mathematical impossibility. Yeah, that's why. So, like, okay, guys, bring it back. So Ashton asked a good question. Is this why light doesn't decay? Yeah, this is exactly why light doesn't decay. So we're talking about, so if you guys don't know what decay is, radioactive particles will decay, they break down into smaller parts. This is the basis for all various types of radiation. So it used to be in Science 10, but you'd say, okay, uranium-235 emits this kind of particle and a little bit of energy, and then the uranium turns into, hold on, where's my uranium? Uranium turns into palladium. Palladium turns into, and eventually all you'll have left is a hunk of lead. What used to be uranium, because the uranium's undergoing decay. Photons cannot decay in particle physics because from their perspective, no time has passed. Like, there is no time for them to decay. The sum total of their existence is instantaneous. There's nothing. Special relativity dictates photons cannot decay, which is a great question. Okay, flip the page. Why didn't we choose to do induction, he says. Okay, this is the last little bit here. Mass is also impacted, because why wouldn't it be? Again, if you actually if this was a true special relativity course, when I studied special relativity in high school, it was a couple days like this has been. When I studied it in university, it was an entire semester. So you get into the background a little bit more, you get into the mathematics a little bit more, you do some ridiculous questions like, if you're in a spaceship traveling at 0.9 C, and you shoot a missile from your spaceship at 0.97 C, we do know that light, like, if we added that together just using classical physics, 0.95 C and 0.97 C, you'd get something that was bigger than C. We know that can't happen, so special relativity has to take that into account. It can't act, nothing can go faster than the speed of light. So there has to be some relativistic effects there that impact the actual speed of our photon torpedo or whatever happens to be for our ship going really fast. That was one of the questions on my final exam. It took me an hour to do that question. But you start to analyze problems like that. The depth to special relativity gets wild. And instead of just saying, oh, this happens, they prove to you why. Unfortunately, I can't do that because you don't have the mathematical backing. So you're just going to have to accept this for me. Things get wild. Einstein has also shown that as objects speed up, there is an increase in mass governed by this equation. M equals m0 over the square root of 1 minus v over c all squared. Which we're going to write down on our formula sheet. It's not exactly the same thing as the last two.
Yeah.
M equals, it's the same as the time one,
Like, same way.
but it's a similar layout.
Yeah.
Square root of 1 minus v over c all squared. And it would be important, the kind of thing that I would toss on the back of the formula sheet that I'm not writing down is who's doing the measuring. We had T was time on Earth observed. T0 is, this is the time observed on the ship. L is relativistic length. Again, if I'm sitting outside of this, what am I observing the length to be as impacted by relativity? L0 would be our rest length. Same thing here. M is going to be our mass as observed relativistically. and m0 is going to be the rest mass. m0 is the rest mass, and m is going to be the relativistic mass. We can write this using the Lorentz factor again, gamma. It's going to look just like the time one involving gamma. M equals m0 over gamma. We'll just do a couple examples really quick and then we'll be done. Suppose an object has a mass of 10 kilograms at rest. What would its mass be if it was traveling at 2.5 times 10 to the 8 meters per second, 98% the speed of light, 99% the speed of light, or as seen in the Large Hadron Collider with protons, 0.999999991 C. Only 2.7 meters per second slower than the speed of light itself. So the LHC is doing insane things with teeny tiny particles. Those are protons. Those particles have mass. Yeah. And this is going to show you why it's so hard to use, well, why you need something as big as the LHC and that draws the amount of power that it does. It's insane how much power that thing takes. So let's do it. We have a 10 kilogram mass at rest, a speed of this. M0 is 10. So m is going to equal m0 over the square root of 1 minus v over c all squared. So that's going to be our relativistic mass equals 10 over the square root of 1 minus 2.5 E8 over 3 E8 all squared. Zach already did it while I was talking. 18.1 kilograms. Pretty quick. At 98% the speed of light, what is the mass of that object? M equals 10 over the square root of 1 minus 0.98 c over c all squared. C's are going to cancel. We're going to get a mass of 50.3 kilos. Good.
No.
99% the speed of light. Let's up it again. 10 over the square root of 1 minus 0.99 squared. 70.9 kilograms. So we're going to go from 99% the speed of light to 99.9999991.
Yeah, that is
74,536 kilograms. All of a sudden now, our 10 kilogram mass weighs 74,000 kilograms. The bowling ball weighs the same. It hasn't. Okay. What is the bowling ball doing? Think about what's happening to the bowling ball. A 10 kilogram bowling ball is getting thinner and more massive. It's not compressing, it's getting thinner. A bowling ball that looks like this now looks like this. The height has not changed. It's gotten thinner, it's becoming a potato. At the speed of light, we've already seen that length, it's going to contract down to nothing, so it would be infinitely thin. So the closer you get to the speed of light, you're not getting taller. Like it doesn't squish you up. You just get thinner in the direction that you're traveling in. So the bowling ball wouldn't even be shrinking this way. It would be becoming like a disc. A discus, someone said, yeah. And its mass is increasing. So it's becoming, do I do it on the next page? I don't. Let's do it right here. What happens if we reach C? If we reach C, m is going to equal m0 over the square root of 1 minus c over c all squared, which means m is going to equal m0 over 0. When I divide by 0, which we can't do, the physical interpretation of that is this. At the speed of light, our 10-kilogram bowling ball would have infinite mass, and it would be infinitely thin, and no time would pass for it, according to the laws of special relativity, which have made sense every step of the way until now. It's the problem, and that's what you got to hang on to. When you're doing special relativity, the thing that you desperately want to cling to is every step we took made sense. So that when you get to the end and you're like, what the hell is going on? You have to cling to the fact that everything you did was valid up to that point. And so your results themselves then must be valid. Special relativity, yeah, see, Nathan, just got to cling to that. Okay? Infinitely thin, infinitely massive, no time is passing. So that is your crash course introduction to special relativity, and I am now officially done teaching you anything new in Physics 12. Congratulations on making it to the end. Okay, so we haven't passed yet, but you have experienced the entire course. You got to prove to me that you can make it through now. I'm going to give you a couple questions out of this. We're not going to do all of these. I'll circle the ones you guys are going to do. We're going to do 2. We're going to do 2, 3, and 4 are all the same. We're going to jump to 5. This is not a challenge. You can do 5.
Ferrari spaceship model X. Ferrari spaceship model X. A friend borrows his spaceship. I just wanted to seem like I'm like fall and Oh, that's not that one.
7's a gooder. Yeah, let's do 7. I want you to do number 9 and number 10. Okay, so 2, 5, 7, 9, and 10. And the rest of the class, ladies and gentlemen, is yours to work on whatever you want. Tomorrow, you guys are writing for me a test on electrostatics, magnetism, and a teeny tiny section on special relativity. Then, those of you who want a shot at proving to me that you can actually do the first half of the course, well, first 6 chapters of the course, the afternoon for you is that final exam. Kinematics, dynamics, energy and momentum, circular motion, and torque. So there's 5. Sorry, there's 5. There's 5. It's on the morning one. Yes, it does. Kind of. It's one big test. It's a true physics final.
Oh, so it's going
in a partial set. The true physics midterm is what you guys are going to experience tomorrow.
So it's going to check my progress.
No, it's going as 3 separate. It'll go in as 3 separate, but you're writing it as one big one. You want it? You want it to go in as the separate bits. Okay? You can work on whatever you want for the remainder of class. Some special relativity. There's magnetism. There's electrostatics. I will print you off more reviews for other chapters if you'd like. Use this time well. You've got almost 2 hours to do whatever is most useful to you. Congratulations on coming to the end. I am sorry we didn't get through induction. You may. Induction's really cool. This is also really cool. Is that the best use of your time right now? Because you got another test coming for tomorrow. Are you writing the test tomorrow afternoon? You're choosing not to write that one. then then I think it would actually be better for you to write that energy test then and to do the review for electrostatics, magnetism, special relativity. That is for your own sake, I think that's what you should do.
Can I take my answer and look
Of
at it?
course you can.
I don't know why.
Let's do it. As you guys finish the reviews, if you want to check anything with me, bring them on up. Here we go. Number 1. Oh, hold on. I gotta make sure I stop recording things.